Okay, I have started the recording. Yeah. So, good evening and welcome to the last tutorial session for the ME75 course, which is Foundations of Computational Fluid Dynamics. So today we will be mainly discussing on only one particular thing, that is the solution to lid driven cavity problem, and mainly we will be going through the way in which we can write a code for this. But the way in which I want to take forward today's class is first I'll just discuss the review of your week 1 to week 7, and then I'll try to share a program, numerical code. I'll try to explain each and every step, and then we can see how it works, the code. And then which is what was done, which was what was done in your weekly material also. So that is the second aspect, and the third aspect will be mainly to solve the tutorial problems, some of the tutorial problems, and then maybe I'll just open the platform for some question and answers regarding the whole course, not only restricted to this week's content. Okay, so first of all, is my screen visible? I have turned on the PPT. Is it visible?
Not yet.
Okay, okay, just let me stop sharing and then maybe reshare. Yeah, is my PPT visible now?
Yes, sir. Now
Okay, thank you. Yeah. So, as I told, first I would like to briefly recap whatever you have learned, because this is like the final week tutorials. So, and this week's content is like a summary of all the week's content, and this week's content is really very important if you are aiming for a career in CFD. This might not be very important for exam perspective, but really when you want to go ahead with CFD and do research in CFD, this is like a foundation stone, this problem. So that is why I want to focus on that. But before that, as I said, let me try to just recap your whole course. Let me try to see how it goes. So basically, in the beginning, that is in the week 1, we tried to understand what is CFD, what is computational fluid dynamics, how is it different from our conventional fluid dynamics, which we have already learned. And I tried to bring in some appreciation for the topic amongst you by sharing some of the practical examples, and I also shared my research topic also, uh, wherein I apply these CFD techniques to come up with a better product. Okay, and also try to investigate new flow physics, try to see what changes comes in with the slight modifications of the parameters, how they are important, I mean practically. So that is the kind of appreciation which I tried to bring in the first week. Okay, so that was just an introductory week, and then we started our business in the second week. So mainly we first saw the Taylor series, how we can expand a function at a next grid point using the values at the current grid point. Okay, so that we tried to see using Taylor series, and we came up with the approximations. I would say approximations. We tried to see the way in which we can approximate a partial differential equation into a discrete equation. Now, what do I mean by that? Basically, if I have something like dou f by dou x, now I cannot numerically solve this dou f by dou x is equal to 0. So I tried to convert this dou f by dou x into some discrete point values. So I know the values of f at, say, at a grid point number 1, grid point number 2, grid point number 3. So how can I evaluate dou f by dou x in terms of the values at these grid points? So that is what we were trying to see using the Taylor series approximation, and that is one of the foundation stone for CFD in general, the basic CFD I would say. Okay, and I expect that you be very perfect, you be very thorough with this particular thing, like how do we convert the partial differential equation into a discrete equation. This is applicable everywhere. Okay, although we saw it in a finite difference method perspective, but I also had explained that even when we go to finite volume method also, and when we encounter the diffusion terms, that is dou square u by dou x square terms and all, we usually uh, have to again come back to do some forward difference or backward difference or central difference, something like that. Okay, so this is very important, that the content which you learned in week number 2. Okay, then going forward in the week number 3, we try to see why we encounter errors with the CFD solution. We saw that the CFD solution was not same as the analytical solution. Okay, and then we tried to give reasons for why our CFD solution was not accurate. Then we saw what are the truncation errors. Okay, and many a times what happens is that CFD solutions diverge, so they are not unstable, they are unstable. Okay, so why they are unstable and why do they give the errors, that is what we try to see using a finite difference method perspective again. Okay, but in the week 4 we slightly changed our path. Okay, so we are coming in a very hierarchical manner. So like in the week 1 we saw which are the various steps. Okay, so I had said in the week 1 itself that first we create the geometry, then we discretize the domain, and then we discretize the governing equation. Now discretizing the domain is very simple thing. You just uh, tend to write what are the different points in a domain. Okay, so like x1 y1 x2 y2 x3 y3 for 2D domain. Okay, say for example if you have a rectangle, then you would divide it into say 100 points in x direction, and you would divide it into say 20 points in the y direction. Then you write what are the x and y values for each grid point. So that is a fairly easy task when it comes to simple geometry. Okay, now the third aspect here was discretization of the governing equations. That is a very important thing, and that is what we were trying to focus in the week 3 and week 2, week 3 and week 4. Okay, so week 2 and 3, as I told, mainly we were dealing with finite difference method. In week 4 we shifted the gears and we saw finite volume method, how it is more physical uh, when it comes to application, and what are the slight changes which we do in finite volume method. Okay, so these were the two things, discretization schemes, which we have mainly learned. Okay, once we got a good hold of that, I had also kind of solved some 1D conduction problems using both finite difference method and finite volume method. The codes are already uploaded on the Google Drive. Okay, in that particular weekly content, you can just have a go through if you need. Okay, then in week 5, we again slightly shifted gear and we came up with like what are different time marching schemes, especially for your parabolic equations. Okay, and why do we need a particular time marching scheme, when does a time marching scheme becomes unstable and all. Okay, that is what we had kind of learned, and that is also very important, especially when you are doing a difficult problem, I would say. For most of the simple problems you can just go with an explicit Euler kind of time marching, that will not create a problem. But when you are trying to solve a difficult problem, you need to consider these factors into account. That is what I would suggest. Okay, so in that aspect, uh, that content becomes important. That is the week I think 5 content, your time marching schemes and all. Okay, so you should definitely go through that also. Now in week 6, I think previous to previous week, right, we studied turbulent flows. How do we model turbulent flows, how do we mathematically model them? and that was a very interesting topic, although it looks a bit uncomfortable, but it's a very interesting topic, because in the nature we see most of the flows to be turbulent, starting from cosmos to our own body. The flows are turbulent in nature, okay, in many cases, okay. So it becomes very important to model them also, and we learned some of the methods, although we did not go into coding for that, okay, because it takes a huge amount of computational resource and all for especially for coding aspects of turbulent flow. So coding aspects we have a bit skipped there, I would say, okay. And then the last week, that is week 7, yeah, I would say again that is a very important content. Why? Because you are learning now how to solve the discrete linear equations which you have got after discretization to get a final solution, okay. So you started from first finding the governing equation for your particular problem, then taking a domain, and then discretizing those partial differential equations on that particular domain, okay. And then finally week 7 you saw, okay, I get the discretized equation. Now what? How do I solve that? There are many methods, and we saw that some of them are very easy, very basic kind of things, like Gauss-Seidel method and all. Like they are just very easy to code also, okay, and they are mostly applicable for many of the problems. But we also saw that when the system becomes tightly coupled, what I mean by tightly coupled is, say for example, you have conjugate heat transfer, you have natural convection in your problem, okay. So what happens is that the momentum and energy equations, they are tightly coupled there, so you get a lot of what do you say, elements in row of a matrix, okay. So in that case, the matrix is not I would say penta diagonal matrix for a 2D. Usually you have penta 5 elements, okay. So you do not get such systems, and it becomes very tricky to solve such problems, and you need to go for a bit advanced method. So there we kind of touched upon preconditioning, what are preconditioners, okay. And then I also had given a hint, although it was not there in the syllabus, I had given a hint of conjugate gradient methods, okay, uh, which are used in your commercial softwares like ANSYS and all. They use conjugate gradient methods, okay. So this was the whole wrap up of week 1 to week 7. I would say all the weeks are very significant because this course is very vast, and foundations of CFD, uh, but it is only for 8 weeks, so the contents are kind of packed up. All the contents are really important, I would say. At least if you are a beginner, okay, I would say at least say your Taylor series, and then kind of uh, trying to see the solution methods and the I mean the stability. These three topics would be more important. But if you are really uh, wanting to create a career in CFD or do research in CFD, then I would say all the topics are important, and the today's uh, content is also very important, okay. So that is what the overall thing which I want to highlight here, okay. So uh, do not try to see these as with respect to your exam perspective, okay. Try to look at them like as if you want to do some work really in this field, and then you would get an interest towards learning these things also. I would say you can skip maybe turbulent flows, okay. Turbulent flows you can skip as of now, but apart from that, the things are important. uh, with respect to exams, um, I don't know, but I really feel that your solution methods, that is week 7 content, solution method, iterative and non-iterative direct solution methods for linear equations, you might get a good number of questions, um, and then maybe the Taylor series, okay, because there the mathematical questions can be framed very um, easily, and then you can be tested uh, properly whether the fundamentals are clear or not, okay. So in that respect I think this is very important, okay. Apart from that, your finite volume method, your convection schemes, How do you choose a first order of point versus second order of point? What are the basic fundamentals for selecting those schemes? You might get you can expect some questions on that regards. This is with respect to exam perspective I am speaking, but in general you have to go through. Okay, so yeah, this is the brief recap I would like to give. So are there any queries with respect to this? You can unmute yourself and maybe speak, or else you can write on the chat box also. You are able to see my this presentation, right? The first slide. Can you write on the chat box?
Yes, we can see.
Okay. I hope everyone is able to see this screen. Okay. Yeah, so that was the first thing. I hope there are no queries with respect to this week 1 to week 7 content. Okay, so that was the first thing which I wanted to touch upon. Yeah, and then the second week you mainly have the solution to the lid driven cavity problem as I discussed. Okay, now the lid driven cavity problem itself is quite interesting. I would explain it in the next slide why it is very important, why and why it is very interesting also. Okay, and then we see one particular method, one particular easy method I would say, and a very popularly used method also to solve this kind of problems. And this is not only applicable to lid driven cavity, this is applicable to all fluid mechanics problems. Okay, and then finally we also saw how do we post process our results so as to make a scientifically relevant and an engineeringly relevant movie. Okay, um, movie, or else you can say story. Okay, both mean the same anyways. Okay, so how can you make a scientifically relevant stories out of whatever results you are getting? That is also very important, right? So you get data. Okay, you get the values of u, v and pressure. What do you do? How do you convey it to a layman, or else even in your field only, how do you convey it? You need to convey it through suitable plots. Okay, not just random plots. Cannot just put velocity and just show, okay, so these are my results. No, that doesn't convey any message, right? For example, if you are doing just a flow over an airfoil, do you plot velocity and then just show these are my results? No, nothing. Nobody will understand. An engineer especially will not understand. Okay, so you need to show him or her the lift coefficient values, the drag coefficient values, how are they changing with respect to the shape of the airfoil. Okay, then there is some understanding. If you are doing some, say, flow over a cylinder for energy harvesting purpose, then you need to show, okay, so this is the amount of power which I can generate from this much of vibration. Okay, so similarly in many other aspects. Okay, so that is why the post processing is also a topic which is not dealt much in this course, but if you are really up to a career in this field, then again I would say post processing is a thing. But I would say that these things, post processing and all, you will understand with experience only. Okay, you cannot get it by learning something like this. Okay, it's not like a textbook kind of material. It depends on your problem statement and all. Okay, so as and when you learn, as and when you apply these course, only then you will learn these things. Okay, so yeah, so why I said lid driven cavity problem is very interesting and very important is that, first of all, it's a problem which is very easy to set up. Okay, you can see that it's just a square cavity, although it can be something else also, but it's basically a cavity. It's a simple geometry, either a square or a rectangle. And what you can see here is that there are three walls. Okay, stationary walls. The top one is also a wall, but it is moving at some constant velocity, say. Okay, this is a typical lid driven cavity problem. There are many variations of this. The bottom wall might be also moving. Okay, side walls might be moving, whatever it is, but these are walls. Okay, these are walls. and you have a Dirichlet boundary condition for velocity. What do I mean by Dirichlet boundary condition? I just have some specified velocity. It's zero on all these stationary walls and it is equal to the x velocity u on this top wall. Now you also have Neumann boundary conditions for pressure, right? So you have a mix of boundary condition, and all the boundary condition are a mixture of Dirichlet and Neumann only. Okay, so you have both the flavors in this problem and they are very nicely set up. Okay, so for velocity you have Dirichlet boundary condition, for pressure you have Neumann, like dou p by dou n is equal to 0. Okay, so that's the boundary condition for pressure which you apply. Okay, and this problem can be applied for both laminar as well as turbulent flows. Okay, so that's the beauty of this problem, and it can be applied to test your 2D and 3D codes. So you have developed a code. Okay, now you have developed a 2D code, say. Now how do you test whether it is running correctly or not? You apply it to this problem. Now you extend it to 3D. Again you take the same problem. Okay, so that's the beauty. Now you are extending it from laminar to turbulent flow code. You basically keep on extending. Okay, so that's the typical workflow in a CFD project. You do not do anything like from scratch only. Okay, first you do 2D from scratch, I would say, then extend the same 2D code through to a 3D code. Okay, then extend the same 3D code to a turbulent flow code. Okay, now you want to test your codes, you have the same problem, then that becomes very easy to set up and easy to see whether you are getting a correct results or not. Okay, so that is why people usually solve this lid driven cavity problem. Okay, the last aspect which is very important is that this lid driven cavity problem can be extended for many other cases also. Like for example, if you are moving from a steady to an transient solver, okay, then also you can apply. How do you do that? This problem inherently reaches a steady state, but if you are changing this velocity with respect to time, okay, it's like a sinusoidal oscillation of the wall. Okay, then you do not get a steady state profiles, you get a periodic profiles. Okay, so it will test the transient code also. Now if you do some modifications to these geometries, say instead of this square you can have a trapezium also, right? Now if you have a trapezium with the same top wall moving, it becomes a complex geometry problem. It's not a simple geometry. You cannot have all the square or a rectangle type of grids. Okay, you either go for unstructured a triangular mesh, or you can have quadrilateral mesh only. It is in a parallelogram shaped cells or something, which they are not rectangles or squares. Okay, so that's the point which I want to highlight here. Okay, so you test for a complex geometry also for the same type of problem. Now you can go to multi-physics also. Okay, you can have a conjugate heat transfer problem. Say I have a difference in temperature between the left and right wall, and say I have a specified heat flux at the top wall and a insulated wall at the bottom with the same problem, same everything else remaining the same. I can again test my code for a coupled Navier-Stokes equation, that is including your momentum as well as energy. I can test the code for the same problem. Now the last case is fluid structure interaction, which I have worked with in my PhD thesis. So we basically, similar to what we do for Navier-Stokes equation for fluid, we solve momentum equations in structural dynamics. Okay, we use some Kirchhoff stress strain transformations, like how you write sigma xx is equal to 2 mu into say dou u by dou x and all those things. So we have Kirchhoff stress strain transformations in our computational structure dynamics. The momentum equations almost remain the same. Okay, so we try to discretize that also, and then we couple it with the fluid. Okay, so what happens is that, assume that the bottom plate is flexible in nature. Now due to the fluid flow, it imparts a stress on the bottom wall. Okay, now this stress is mainly pressure stress and the shear stress. Okay, this kind of oscillates the wall because it is flexible in nature. So it is a coupled problem, and due to the oscillation of the plate, there is a change in the flow pattern also. It's not the conventional driven cavity flow pattern. Okay, so it's a coupled problem. So that was the first solver which I developed in my PhD thesis, the coupled fluid structure interaction. Then I extended it to acoustics also. Uh, okay, so this problem can be used to test my FSI case also. So this is just I have put a simulation of my fluid structure interaction code. Okay, so you can see that this bottom wall, it is vibrating because of the fluid stress. I have considered this bottom wall as a flexible. Now you can see that this oscillation of this bottom plate will also have an impact in the fluid flow pattern. Okay, so this is a coupled problem in a sense. Okay, so we can test. Now there are benchmark results available for this case also. Okay, so this is the first case which I had tested, okay, when I developed an FSI solver, because this was easy to set up also. Okay, although I have done again validations for many other problems, and they also involve somewhat lid driven cavity only. So in lid driven cavity, at the center they place a flexible plate. Okay, again it's the same thing only, and both walls are moved, top and bottom. How does this flexible plate move? Okay, oscillate. Okay, those things also we can study very well. Okay, or else you fix a plate, flexible plate at the bottom wall. Okay, and then how it can move. It is like a movement of your plants in the your marine bed. Okay, so in the shallow waters, how they move due to the waves in the ocean, something like that. So people do study those aspects also. Okay, so you can extend it to multi-physics also, this problem. So that's the beauty of this problem, and although it looks very simple, there are many extension of this problem, and it is a very good problem to test your code. Okay, so that being said, let us try to see how we can solve this problem in today's class. Okay, so we have mainly looked upon one particular algorithm in this weekly content. That particular algorithm was pressure projection algorithm. Right now, there are many algorithms which you have already studied. I think you have, I think, the simple algorithm which is very famous and it's used in commercial softwares also. Okay, and then you have Mac algorithm, and you have simpler. Okay, and then I had said it in the previous weeks also that pressure projection is the most easy, and I do not know why it is not applied in many situations, but it can be applied. And in my whole PhD thesis I have applied pressure projection algorithm only, and that was what was discussed in the week 8 contents also. Okay, so it's a very nice to solve kind of algorithm, and it's very easy to understand also, which you will see. Okay, now I will explain why it is easy. Okay, just before getting into the questions for today's class. Okay, now you can see, basically I want to solve this equation, right? Rho into the discretized momentum equation, x momentum I am writing discretized version. Okay, sorry, I do not have a mouse today, so I might be a bit slow in writing. Okay, so this you have divided by delta t. Okay, you have an advection term, you have advection. Okay, I'll just write it as a is equal to, you have a pressure term, right? So just let me write it as gradient of p. This is again in x direction only. Okay, just take it as it is, plus diffusion. Now what do I do is that I'll just substitute, instead of un plus 1, I'll just substitute star. Okay, and I will not include this pressure gradient term. I will completely ignore this pressure gradient. Without this, let me just calculate u star. So you will get u star in that way. Now if you subtract these two equations while taking un plus 1 and while taking u star, what do you end up with is un plus 1 minus u star. Okay, you can see it from here only. If you just subtract these two equations, you will get On the left hand side you will get un plus 1 minus u star only, right? Whatever divided by delta t, those things will be there anyways, into rho, everything will be there. Now what you see clearly here is that the advection term, it cancels out because you are subtracting these two equations. Advection is present in both the equation and diffusion is also present in both the equation. What remains is only the minus of okay, it's actually minus of dou p by dou x only. Okay, this is for x momentum equation I am speaking. So only this term remains out, and this we know it is at n plus 1 time level because velocity and pressure are coupled, that we have already discussed in the previous weeks. Okay, so this will be at n plus 1. So did you understand how we get this equation, the last equation which I wrote here? Are there any queries? You can write in the chat box if there are any queries, or you can say also. This is very important, and I think it is very easy also to understand. Okay, yeah, I hope there are no queries. I don't see any messages. Okay, so when you subtract these two, you get this particular equation, right? Because advection is there, diffusion is also there, only the dp by dx was missing when I took u star. Okay, so I have just subtracted. Okay, so now what do? I apply divergence on both LHS and RHS. Okay, divergence operator. So this is for x momentum. Okay, similarly I'll write for y momentum. What I will do is that I will take dou by dou x of this equation, and then y momentum whatever I get, I take dou by dou y of that. Okay, now what you see is that dou by dou x of un plus 1 plus dou by dou y of vn plus 1, that is according to continuity it will become 0, right? So what you will end up with is minus rho upon delta t, okay, into divergence of u star only, right? Because this divergence of un plus 1 will be 0. Divergence of u star will not be 0 because we have ignored gradient of p while calculating this u star. Okay, so it's not it does not satisfy the continuity, so there will be something which is left. Okay, this will be left. Now on the right hand side, what will be left? Minus of, you are taking this with respect to x, right? Dou square p by dou x square. Similarly for the y momentum, you take dou by dou y of dou p by dou y. So you will get Laplacian of pressure, right? Del square p at n plus 1. So this is the called as pressure Poisson equation, and this is what you have to solve. Okay, and you know how to solve it because u star we have already calculated, so I know this left hand side term. Only the right hand side term I do not know. I apply just a Gauss-Seidel rule. Okay, I will discretize this using a second order central difference scheme. I'll get pi uh, pi at say east minus 2 pi at present plus pi at west. Okay, so whatever it is, so that I will discretize it and then I'll apply just a Gauss-Seidel solver, okay, which we have learned last week to get Pn plus 1. Now once I get Pn plus 1, you can very easily see, I will come back here again. I will just say un plus 1 is equal to u star minus delta t by rho into dou p by dou x. This I can do because now I know Pn plus 1, right? So this is as simple as that. In simple algorithm and all, there are some multiple steps involved, but this algorithm is as simple as this. It's a 3-step procedure. Find u star, solve the pressure Poisson to calculate pressure, update the velocities. Yeah, that's the 3-step procedure. Are there any queries with respect to this algorithm? Okay, and can you comment on what type of time stepping we have used here? Can anyone comment on that? What type of time stepping we have used here? You can maybe unmute and say also. Yeah, yeah, yes. Forward. No, no. Time stepping, not the discretization scheme. Time stepping schemes, see, there are three types of time stepping schemes. Now you have explicit time stepping scheme, implicit time stepping scheme, and you have Crank-Nicholson scheme. Forward and backward, that is for spatial discretization, I think you are telling. I am asking about the time stepping. Forward means maybe you are telling this is Euler forward, something like that. Okay, that I can agree, but I am asking overall. Huh. So Ayaz saying explicit, Ravi Karan is saying implicit. Okay. Ayaz, why do you think it is explicit?
There is it one equation, one unknown we are finding at n plus one,
Hmm.
not and not taking average of two times.
So you are telling because we are writing A and also here, right? Maybe that is why you are telling explicit, right?
Yes, yes.
Yeah. Okay. And why Ravi Karan is saying implicit?
Yeah. Actually, uh, I because the second equation it has both n plus one
Yes,
both
yes,
sides.
yes. This is the confusion. In the weekly content, I saw that it was given explicit, but it is neither explicit, neither implicit. It is called as semi-explicit scheme. This particular scheme, it is not explicit, it is not implicit, it is not Frank-Nicolson. It's a semi-explicit. Why? Because you are taking all the terms except this pressure at n time level. So in that regards, it's an explicit scheme. But you are not taking pressure at n. Okay, you cannot take also because they both are coupled in a sense. You will get false answer. Okay, so it is called usually as semi-explicit pressure projection scheme in literature. Okay, it's called because here, as Ravi Karan said, there is n plus 1 also. Okay, so pressure we take it at n plus 1. Apart from that, all we take it as n. So only pressure we take it at n plus 1. So that is why it is called semi-explicit. Now, what if I took, say, for example, the advection term at n plus 1 and diffusion term at n plus 1. Okay, is this even possible? Can you comment on this? This would become a fully implicit scheme. Okay, in reality, this is not possible because advection has u into dou u by dou x. Now, it will become a non-linear equation, and with the methods which we have employed in the current course content, it's not possible. You have to go to solution of non-linear equations. Then maybe you could use Newton-Raphson method or all, but those things are usually not used because they run into stability issues. Okay, so we avoid this. I have not seen, I have rarely seen any non-linear solvers being used for Navier-Stokes equation. Although it's very common in structural dynamics, it's not very common in fluid dynamics. We do some compromise. Okay, the compromise is that this d we take it at n plus 1 because there is no harm in doing so. We have dou square u by dou x square term or dou square u by dou y square that we can easily write. It's a linear term only. Here it becomes a non-linear term. Okay, so what we do, what compromise we do is that this is usually termed as mass flux term. Okay, this mass flux we take it from nth time step only. Okay, this mass flux we take it at nth, and this dou u by dou x or whatever dou u by dou y whatever is there, that we keep it at n plus 1, and this method becomes what is called as semi implicit. still it is not fully implicit, but it is more close to implicit. Okay, so that is why that scheme is called semi implicit. Okay, now people have come up with an another alternative, okay, which makes the scheme fully implicit, but at the same time we are solving linear equations only, and that's a very I would say a very intelligent thing to do. Okay, so what people have done is that, okay, let me keep this at un only. Okay, but within a particular time step n, I will do multiple iterations. Okay, so this will be at first iteration un1. Okay, now I go to second iteration. Now I do not take from previous time step. At the given time step, I take the value of u from previous iteration k. Okay, in the second iteration. Now in the third iteration, I take the value of u from second iteration within one particular time step, I am telling. Okay, so in that way what I do is that I'll take u in this current time step only un plus 1, but at a previous iteration. Okay, this people usually call it as fully implicit. This people usually call it as fully implicit. Okay, they are trying to make it implicit by doing multiple iterations within one particular time step. Okay, otherwise what would have happened is that in a one go we usually calculate u star, and within one go we usually calculate v star. That would not be possible. Okay, what we have to really do is that we have to solve all u star, v star, okay, and then the pressure Poisson, and then again come back and then use the previous iteration u. Okay, we have to update the value of u and then use it again in the mass flux of the advection term. That would make it fully implicit, but let me tell you that is out of the scope of this course. Okay, so don't worry much about this fully implicit, but I hope that you have at least understood what is semi explicit and what is semi implicit method. Okay, at least those two things uh, should be clear to you. uh, are those two things understood? I mean, semi explicit and semi implicit method. Okay, if there are no queries, okay, okay, yeah. And one more thing, I think Anthony joined just now. Anthony, you had asked me a question last week regarding the order of accuracy of for this polynomial method, and I think I gave you kind of a very long method to reach the answer. Okay, but I think I realized it later on that there is a much simpler way. So whenever you do a polynomial method, say you write t as a function of ax square plus bx plus c, right? Okay,
Yes, sir.
quadratic. So it itself, this scheme, whatever you do, it becomes second order in nature. Okay, that's the whole fundamental reasoning why we take ax square plus bx plus c, or sometimes we can take only ax plus b or something like that. You have to see what is the order in that dt by dx, t square t by dx, I
The
think.
maximum order.
So in that way also you can, I think, determine.
So if t is equal to ax plus b, that means the order of accuracy will be 1.
Yeah, 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 if you are taking the function like that.
Okay.
So that is also one of the, and that is, I think, the I think the correct way. That is why, that is how you are formulating a polynomial, right? I mean, what is the basis of taking ax cube plus bx square? What is the basis of taking ax square? That was the reason, I think. So that is how you, I think, get it. Okay. But once again, you
Thank you, sir.
just clarify that also. Okay. But what I said, that is also applicable last week, but that's a very tricky and very like a long path, I think. This should be more easier to do, I think. Okay. Yeah, so let us go into today's questions, and once I discuss these questions, I'll just show you an implementation of whatever I discussed now, the semi-implicit pressure projection method. Sorry, I will be doing semi-explicit pressure projection, which was discussed in your weekly content also, and that code I will upload on the Google Drive also. You can also play around. There are some issues with that code which I have written. I'll tell those issues also, you can correct on them, but apart from that it gives a fairly accurate result. Okay. Okay, so question number 1 is a true or false question. In a lid driven cavity flow, which we have discussed till now, uh, is it possible to capture secondary vortices of size less than grid sizes? Is it possible? True
Sir,
or?
the secondary vortex means one from the corner.
Yeah. So basically, I had indicated in this diagram, I think. So basically, you have one main recirculating zone in the center of the cavity, and that is usually called as a primary vortex. And in the corners, you have some small recirculation zones. Those are usually called as secondary vortices, but it's just a terminology anyway. Can you write down the answer on the chat box? Yeah, less than the grid size. That is what they are asking. Yeah. So it should be false. So basically, what happens is that any vortex you take, okay, the thing is that it has the recirculation zone. Now, what do you mean by this recirculation zone? Is that the velocity here changes from uh, negative to positive or positive to negative, whatever it is. It has to change the sign like this. So the flow has to go in a circle, okay, in a vortex. Now, when it is changing the sign, it has to go from negative to positive, and at one instant it goes to zero also velocity. Okay, that is not possible within one cell. Okay, within one cell you will get only one velocity value, right? So you cannot go from a negative to positive. Okay, at least you need two cells to do that. Two cells would also be not accurate actually, because you'll not get zero, but anyway you can manage with that. But within one cell, uh, whose size is less than delta x delta y, definitely that's not possible. Okay, I think you have answered on the chat box quite correctly. Okay, now let us look at the second question. Again, a true or false question. True or false question. Laplace equation is a parabolic equations, hence we need boundary conditions. Is it true or false? First of all, Laplace equation, is it a parabolic equation?
It's elliptic.
Yeah, it's an elliptic equation, right? So basically, Laplace equation is what is given here. Like you have basically 0 on the right hand side, it's just the dou square t by dou x square, or any dou square phi by dou x square plus dou square phi by dou y square is equal to 0. If there was something on the right hand side, then we usually call it as Poisson equation. Okay, and that is what we saw in our pressure projection method. For pressure we get a Poisson equation and we call it as pressure Poisson equation there. Okay, now it is 0 for this yeah, Ayaz, you want to ask something?
Sir, if you have to make this the transient one, so del t by del time will be added in the left hand side or right hand side?
No, no, I did not get you. You want to add what transient term?
So
A transient term, it will be added on the right hand side only, na? Because you have what do you have? Dou t by dou t plus the advection. It is like similar to momentum only. Is equal to diffusion. That is diffusion. The Laplacian term is like a diffusion term. Dou t by dou t plus your advection term is equal to diffusion, na? So dou square t by dou x square is a diffusion term. So it will come on the other side. Both are
okay,
on the. Uh,
but in the slides, actually it is mentioned on the left hand side. So I had this query.
No, no, dou t by dou t, okay, it is on the left hand side. Then diffusion term, Laplacian term will be on the right hand side. What I'm telling is both will be on the opposite side.
Okay.
They will not be on the same side, but this, see, usually we write it like this, right? Equations. So dou t by dou t will come on the left hand side, and say diffusion term will come on the right hand side. Anyway, we can write it other way, but what I'm trying to tell is they come on the opposite side. They cannot come on the same. You cannot have plus dou t by dou t. That is what I'm telling.
But it's there in the slide.
What is there? Dou square t by dou x square plus dou square t by dou x square plus dou t by dou t.
Yes, sir.
Ah, no, no, that is wrong, I think. That cannot happen.
Maybe typing error.
Yeah, it might be typing error. Minus should come definitely. Okay. Yeah, so if we compare it with a standard format of equation, a into dou square t by dou x square plus b into dou square t by dou x dou y plus c into dou square t by there are other terms also, like we have dou t by dou x only, dou t by dou y only, but let us see only with ABC. So these are the ways in which we can find A, B and C to determine the characteristics of the equation. Okay, so here B will be 0 because we don't have mixed derivative, sorry, and A and C both are 1. So B square minus 4AC will be minus 4 less than 0, and it's an elliptic equation. So parabolic, it should be equal to 0. So false, directly it's a false. Okay, and usually when we have parabolic equations, what happens is that usually they are transient equations, and what happens is that uh, we usually need initial conditions also apart from boundary conditions. Okay, so that is also required for a parabolic equation usually, because they turn out to be transient equations, and transient equations need to have initial values. Okay, so let us see question number 3. In the numerical solution of lid-driven cavity problem with explicit discretization for both space as well as time, okay, the stability of the solution is dependent on which of the parameters? Okay, you are solving a lid-driven cavity problem as I discussed with explicit discretization. Again, it's not purely explicit, it is semi-explicit because pressure we are taking it in n plus 1. Usually in the literature, whatever I have referred to, usually people mention it as semi-explicit. Okay, so we are solving it with a semi-explicit discretization. Okay, and so what are the factors on which the stability will depend on? That is the question. Time step size, lid velocity, and grid size. Which of these will determine? So what should be the answer? Okay. Hmm. So two of you have said B, as you have said D. Okay, let us see what's the answer. Okay, so basically I have told this initially also that there is something called as CFL criteria. Okay, which kind of determines what should be the time step size for a stable scheme. Okay, you can read it the other way around also. What should be the smallest grid size to ensure a stable scheme for explicit time marching? Okay, now the CFL criteria, it is calculated as follows. It is calculated as u into delta t by delta x. Now CFL number that should be less than 1. So that's usually for true for semi-explicit discretizations. Now we can debate it, but the thing is that delta t is time step size, very obvious, and delta x is the smallest grid size, and u is exactly not lid velocity, but it's a characteristic velocity, but that characteristic velocity is determined by the lid velocity. So lid velocity also does play a part in determining the stability of the solution. Now usually what we do in our CFD codes, let me tell you that. Okay, so we also do not go with the fully implicit as I explained it. Why? Because fully implicit will involve, although I have personally written a code for fully implicit, but the thing is that it takes too much computational time. So I also usually go with semi-implicit pressure projection. It's not semi-explicit, it's semi-implicit, and semi-implicit pressure projection also has a stability problem. Okay, we need to ensure u delta t by delta x is less than 2. Okay, not 1. For a semi implicit, it is a bit higher. Okay, for explicit it is usually 0.5 or 1, I don't remember, whatever it is. Okay, so the thing is, in my code, what I do really is, say for example I have this lid driven cavity code. Now I have divided it into many grid points. So at each grid point, okay, I keep on checking, okay, what is the value of u delta t by delta x at every grid point, huh? because the thing is I can have a different grid spacing, okay, and I do have different velocities at the internal grid points, and CFL number is for each grid point actually, okay, and then we check maximum of CFL whether it is going beyond 1 or not. If it is going beyond 1, it will not converge. What we have to do is we have to bring down the delta t time step size. That is what we usually do. Okay, so now what I do is that once I have a lid driven cavity problem, I know the lid velocity, say for example 1. So based on this I'll guess what will be the maximum lid velocity, a maximum internal flow velocity. Now that will depend on the lid velocity. Lid velocity, if it is 10, I will have somewhere around 15 meter per second within the internal flow. And that I will take it as velocity scale. I will not take exactly the lid velocity, something higher than that. But if I had a lid velocity of 1 meter per second, okay, then I would take the characteristic velocity as 1.5 meter per second. Okay, understood? So that is how lid velocity will also play a role. That is why I have written not exactly, but it does scale with lid velocity. So lid velocity will also have a role apart from time step size and smallest grid size. Is that clear?
So what is CFI?
It's Coran Frederick some number. Okay, exactly. I also do not know the full form, but the thing is that you need to have this diffusion terms. Okay, so they have to not grow exponentially when you do this von Neumann stability analysis and all. Okay, you will come up with that, and usually uh, there was a person who kind of uh, Courant Frederick's Levy condition. Okay, this was a person uh, who kind of okay came up with this number. Okay, and he said that okay, so you are able to see my screen, right? Okay, so he came up and he tried to derive this. Okay, based on that uh, stability analysis, and then he said this u delta t by delta x, it should be less than C max. C max will depend on your time stepping scheme. Now this is zero point 0.5 I think, not 1 also, for an explicit time marching scheme or something like that. That is given I think here. Uh, somewhere it was given 0.5, and for my semi implicit is 2 usually. So that is what we check. Okay, and you should know how it has come. Maybe you can go through the derivation also. Okay, but this was I think the person who end up came up with that. That understood?
Yes, sir.
Okay.
So this criteria determines the stability of the
Solver, yes.
conjugation.
Yeah, this is very important. We do check it at each and every time step. I do check what is the CFL number in my code, because if your CFL number is going beyond 1, you will go into divergence. That's for sure. Okay, even I think ANSYS does not have fully implicit time stepping. It also has semi implicit time stepping. So there also you need to consider the uh, time step size properly, otherwise you will run into divergence. Okay, so it depends on all grid size, time step size, and lead velocity. Okay, so let us go to the next question, that is which of the following is the correct representation of u velocity in the corrector step. So we have predictor step, then we have a pressure Poisson step, and then we have a corrector step, right? So in the corrector step, what we do, as I explained it just now, we correct the velocity from the predicted velocity using the knowledge of pressure, okay, which we have got using Poisson equation. Okay, so how do we correct that? I also had given the equation for that. So just can you discretize that and just tell me what is the correct answer? So I here, I think I okay, I am also getting confused. Yeah, I here indicates x direction, and j indicates y direction, because in my code usually I write the code in other way, because I think is rows and j is column in MATLAB. So here and there it becomes confusing. Yeah, but I is x index. Okay, fine. So I am getting a mixture of answers among A and B. Okay, okay. So I explained it, I think just now. Should be there here. Mm-hmm. Huh. Think it's there here, yeah. So when I subtract these two equations, un plus 1 minus un divided by delta t, I take the other equation is u star minus un divided by delta t. So I have two equations. When I subtracted them, this un will get cancelled out. What you will remain with is un plus 1 minus u star and only minus dou p by dou x. This is for x momentum. Okay, this much will remain. So you will take un plus 1 is equal to u star minus dp by dx. Okay, minus dp by dx should come. So minus should be there. So that is what I have written. I think I take these two equations. I hope this is understood. This is the advection term. This is the diffusion term. It remains the same here, whether you take un plus 1 un. Okay. Only when I take un plus 1, I have dou p by dou x term also. Okay. Now when I do subtract these two equations, 1 minus 2, as I have written, sorry, it is 2 minus 1. I come up with like this un plus 1 minus u star divided by delta t. So un plus 1 is equal to u star minus delta t divided by rho. Okay. So B should be the correct answer. Yeah. So the fifth question, let us stop with fifth question because sixth and seventh are like almost similar and they go well with this whatever we have discussed. You can go through the slides. So this will be last question. I will just discuss the code and open the platform for question and answers. Okay. So which of the following is a correct explicit discretization for convection term for compressible lid driven cavity flow? Yeah, I forgot to say that. Maybe I have not, because I personally have not worked with compressible flows, uh, but this problem again can be applied for a compressible situation also. Okay, so what should be the answer for this? Okay, you all are telling B. Okay, so what I know is the convection term for incompressible and compressible will not change. Okay, because see, incompressible or compressible, the in the momentum equation you have an inertial term, right? What does it indicate? Rate of change of mass. Mass is written rate of change of mass. It's just um, into acceleration, right? So rho into delta v into you get dou u by dou t. This is actually a material derivative. Dou u by dou t. This is nothing but your mass into acceleration term, right? And that is what Newton's second law, the total force is equal to mass into acceleration. So whether it is an incompressible or a compressible doesn't matter, mass is outside of acceleration. Okay, so you get really rho into dou u by dou t only. Okay, per unit volume, this is all volumetric, so per unit volume, so you only get this much. Whether it is compressible or incompressible, it should not matter. So rho will not come inside this. Okay, so many times we do have this confusion. This is true for the your what say continuity equation, and we do not have time there. Okay, yes, that's a different story. But in momentum equation we have mass into acceleration. Mass, I'll write it as usual, na, rho into delta v. Now I have volumetric, so I'll write only rho, and for acceleration I'll write just material derivative of dou u by dou t. Okay, it's the same. Okay, now so what happens really here is that you get rho into the partial derivative, the local derivative, dou u by dou t. Okay, then you again land up with same incompressible thing only. Okay, when you have a compressible governing equation, your diffusion terms will change. Okay, there are a lot of extra diffusion terms which come in, but this advection part, as far as I have read, okay, it's the same only. Okay, so again rho u into dou u by dou x only. Okay, but what happens in incompressible is that I think people do try to put this u inside also, because again we can simplify it and make dou u by dou x plus dou v by dou y is 0, which we anyways know. Okay, so that is called as a conservative form. People try to bring it in conservative form. Okay, but anyway, the truth is that it remains the same, whether incompressible or compressible. So in that sense, A should be correct. Okay, I don't know about D, whether D should be correct. Why? Because I don't think D should be correct here, because in a compressible flow you have rho which is also varying with respect to space, right? Compressible flow. So I cannot with this equation what is written here, I cannot just simply pull out rho outside this derivative term. Okay, that would have been possible for a, I think incompressible,
Incompressible.
yeah, but here I don't know. But is there anything else you want to say? I mean, I don't know why D.
Maybe compressible might be varying with respect to x and l, y. So that's why. Yeah.
Yeah, maybe I'll have to check whether we can, like, because in incompressible people do try to bring it like this. Okay, using the incompressible condition, they write rho outside only anyways, not inside. They write dou by dou x of u square plus dou by dou y of u into v. Okay, like second option, the second option is there, na? Usually people write anyway. Second is not correct. I don't know how the second one is not correct. This people try to write, but I don't know whether for compressible also we can do. I think because dou by dou x of rho u plus dou by dou y of rho v will become 0 for a compressible. So I think, yeah, that should also be possible. I think, yeah, rho v. Uh, just hang on for a second. What will happen if we consider rho v as one term? So un will come out. Here also un will come out. Yeah, yeah, yeah. That will also be correct then. Yeah, D will also be correct. Yes. Uh, because un will come out, and what will remain is dou by dou x of rho u plus dou by dou rho v. Yeah, that will become 0. And the other terms which will be remaining is anyways, here you have taken un common, so rho v into, yeah, rho v into dou u by dou y here. Yeah, rho u, yes, correct, you are correct, Anthony. So I think D will also be correct. Okay, so D will be also correct, and then A will be also correct. I think, Anthony, think you have correct, what you have said is correct. Okay, what I initially had in my mind was that A would have been correct. But along with A, I think for this question, D is also a correct answer. Because similarly, in incompressible flows also, I have usually seen that people try to bring in dou by dou x of u square plus dou by dou y of uv. So here for compressible flows also, we can do that kind of stuff. Okay, so both answer A and D should be correct for this question. And Siva, you have asked a question that will not density change when there is a change in pressure. See, that is what I was trying to explain it here. Okay, so there will be definitely changes in the momentum equation. It will not be same as the incompressible flow, but we are trying to see the convective term in the question, and it is just the mass into the acceleration. Okay, now the mass itself, it can be written as rho into v, and acceleration as dou u by dou t. Okay. Now there is no change with respect to compressible or incompressible here. Okay. And since we are taking volumetric, this v will also go. Okay. What I remain on the left hand side is nothing but rho into dou u by dou t, which is same for compressible or incompressible. The changes will happen on the right hand side where there are diffusion terms. Okay, so basically what you have is that in tau xx, or as you call it as sigma xx, I think in sigma xx what happens is that you take it as minus p plus 2 mu into dou u by dou x, right? In the conventional incompressible flows. Okay, 2 mu into dou u by dou x. So sorry, this is for incompressible flows. In compressible flows, you also get here one more additional factor, minus 2 by 3 mu into divergence of velocity. Okay, This is the extra term which you get for compressible flows, and you do dou by dou x of this term in the momentum while deriving the momentum. Okay, so everything will change here. Okay, so this is the whole thing which is changing. Okay, in compressible and compressible, but in the convective part things will not change. Okay, so A and D should be correct for this. So as I said, the question 6 is also on the accuracy for discretization that I've already discussed in the previous question. But anyway, these slides I'll be uploading on the drive. And similarly, how do we take the indexes for calculating the um, north face velocity? That is a seventh question, and eighth question is fairly easy. This is why we have taken a central differencing scheme. Is second order accurate first of all, and we have taken both forward and backward indices because we have assumed that the diffusion is isotropic, that it is same along all the direction. Okay, so that is the answer. So those are the 8 questions which I wanted to discuss anyways. So let us come to the coding aspect. Okay, I had said this initially also that my code is not perfect as of now. I'll tell why it is not perfect, but you will get fairly accurate results even with this code. Okay, and I will upload this code, okay, on Google Drive. You people can go check and modify this code to make it perfect. Okay, I will leave it to you. It's your, I mean, your interest. If you want to do, you can do. Otherwise, just see the code. Okay, so let us come from the beginning. So in a first step of the CFD is to do pre-processing. It's called as pre-processing, wherein you define the domain, you define the number of grid points, you define the geometric parameters. Okay, so basically I have defined the domain by using this length of the square domain. I have written L is equal to 1. So nx ny indicates the number of grid points. Okay, dx dy grid spacing. Now the time parameters, this is the final time where I will be stopping. Ideally I should not do this because this is a steady state. I should stop it when the difference between two time steps becomes less than tolerance, but just in case that does not happen, I am forcefully stopping the simulations at t is equal to 20 seconds, and I have taken a very small time step size b is equal to 0.01. Now this is not the correct way. Okay, this is not the correct way of um, writing the time step size. Ideally what you should do is that uh, delta t, okay, let me write it something else. Delta t is equal to I wrote the CFL criteria right here, u into delta t by delta x. I don't know where I wrote. Anyway, okay, leave it. U into delta t by delta x I had written. Okay, so it should be less than that, so I'll take 0.5. It should be less than 1 I had written, so I'm taking 0.5 into dx, okay, divided by u characteristic, which is 1 velocity. Okay, so that is how I usually calculate dt value. Okay, and this should be ideally less than 0.5 also. 0.5 is a critical value. In CFT we take it as 1. This is how we determine dt value. Okay, this is the correct way. Okay, but here just so that I get a smooth results, okay, just for understanding I have taken a fixed value here. And nu is nothing but your kinematic viscosity. Okay, that is I have set to 0.01. Now the Reynolds number you can see will become 100. Why? Because length is 1, velocity of the lid is 1, kinematic velocity is 0.01. So 1 by 0.01, Reynolds number is 100 for my flow. Okay, now I have defined all the velocities u, v initial. I am initializing u, v, p and p old. Also I need to initialize u star and v star also, but I have done that in the next step. Okay, but before that I have defined the velocity of the top lid. Now this is what I was telling, that my code is not perfect. Can you tell me why this is not perfect in the chat box, or you can unmute and say. Can you write down on the chat box or can you unmute and say why this line is not correct, which I have marked here? So these are things which you have to understand. I don't know, you people might be kind of referring through this course with respect to some exam perspective or something like that, but these are the things which really matter and which are very important. Okay, the coding aspect. Okay, so try to focus on coding also. I don't know how many of you are really practicing, but I have uploaded many codes. Okay, and I don't know how much you have practiced or not. Okay, grid has to be generated. Okay, grid. See, the thing is, I am indirectly generating the grid here. Okay, so I am telling length is equal to 1. I am telling dx is equal to 1. Okay, all those things are done. So what I have written is define the ghost cells near the boundary. So you don't. I don't know whether you have really gone through the course contents or not. So sorry. It should be a straight line. Okay, again, it's not coming straight line. Sorry, I don't have a mouse today. I'm just using my touchpad here. Okay, so basically, have something like this. Okay, so what happens is that you store P here, right? And you store velocity somewhere here. Okay, now your lid is here. Okay, it's the top. There is no cell for velocity here. You define something called as ghost cell. Okay, and what you do is that you make the velocity 0 here by saying that these two velocities average should go to 0. That how do you do? See, if this is number ny minus 1 grid point, okay, and this is nyth grid point. Okay, now I do not have a perfectly matching grid point on the lid. I have for y velocity, that I can directly write. For u velocity I do not have, but I want to implement that u velocity is 1. So average of these two, u at ny plus u at ny minus 1, okay, divided by 2. Okay, sorry, divided by 2 is equal to 1. This is the whole implementation of your Gaussian method. So now u at ny should be equal to 2 minus u at n minus 1. Okay, I have directly written what I have directly written, I have directly written u at ny is 1. Okay, this is crudely, this is correct when you have a very high grid points. Okay, what I am trying to do is that I am just trying to tell, okay, see here and here I have same velocities. Okay, 1 1 1, take it 1. Okay, just I am like forcefully pushing it. Okay, but this is not the perfect way to do it. Okay, but with this also you will get fairly simple accurate results. Okay, that's the problem. You should try to improvise this is like an assignment. Okay, for you people, you should improvise on this code. Okay, apart from that, these are the boundary condition, because there are no other boundary condition. There are like velocities are 0. Okay, so there also you have to be careful. I have forcefully put it to 0 because I did not define anything, but you should take the average to be 0. Okay, and then I get into the time marching, wherein I initialize in the starting u star is equal to u, and then I calculate u star here. Okay, now u star, u star minus un divided by delta t, that was equal to minus of advection plus of diffusion. You can clearly see that there is no pressure term involved here. Okay, this is just advection and diffusion I am writing. Similarly, v star I am calculating. I am just using a second order central difference for diffusion, and then a first order, sorry, a central difference, that is a linear interpolation for calculating the values of variables at the phase. Okay, and then I'm calculating this is nothing but divergence of u star, sorry. Okay, that I'm writing it as p, and I'm then passing it this dx dy and p hold, along with that the RHS term in the pressure Poisson, this is b, that I'm passing it to a pressure Poisson solver. Now again I'm calling, this is the definition of that pressure Poisson solver here. Okay, so what I'm doing, I'm just doing a Gauss Seidel method here. Del square p is equal to this p, okay, b, whatever was there, whatever I had passed in here. Okay, so this is how you really implement this. Again, there is a issue here. Okay, can you point out what the issue is here? What was the right hand side, actual right hand side? I think I have written it somewhere here. When you do pressure Poisson, divergence of del square pn plus 1 is equal to rho by delta t, right? Rho by delta t of divergence of u star. Okay, so that is not present here because I had taken initially delta t is equal to 1 when I ran the code, so that had worked. Okay, so you have to take this account, because when I calculated b, I told you that I just calculated divergence of u star, I have not done anything. Okay, divergence of u star, okay, this is what I have calculated as b, but it is not just that, right? I mean, the b term is not just that. Okay, it also includes rho divided by delta t. Anyway, rho is 1, doesn't matter, delta t I had taken 1, and then okay, so ideally you should have dt I wrote, or what? Okay, let me do one. Okay. Okay, that is how I am implementing Gauss Seidel. You know already how to implement it. We have already solved, I think, a 2D conduction problem using Gauss Seidel. So this is very similar to the 2D conduction only, but only thing is instead of 0, I am having this p by delta t. Apart from that, everything is the same. Okay, just let me keep it running when I am explaining, because it takes too much time to converge. Okay, okay, I think there is something issue. Okay, I am not passing in. Okay, okay, I am not passing in. Let me just hard code it then. Yeah, this is what happens. I had hard coded it at 1, I think, initially, so I just left it like that. But you should be very careful. You should send delta t properly. Okay, and yeah, so this is all about pressure Poisson. That is the second step. Okay, that is the second step. U star V star calculation first step. Second step is pressure Poisson, and you can see that I have kept it 0.8 into P. Okay, I am starting the pressure Poisson with the previous time steps pressure, but I am slightly under relaxing just not to overshoot and go into divergence. Okay, you can see that the results are also converging here. It has already reached the residual of 10 raised to minus 6 now. Okay, so and then the third step, fairly easy, it's just u is equal to that u star minus dou p by dou x, v is equal to v star minus dou p by dou y. That's it, you are done with the code. Okay, then this is just I am calculating the whatever tolerance, whether it has reached or not. Okay, what I am telling is that if the difference in the velocities, if it is less than 10 raised to minus 8, then just break out of the time loop. Okay, otherwise it will continue till the maximum time is reached. Okay, maximum time I have written t, that is 10 seconds here. Okay, if it is reached, it will stop automatically, otherwise it will reach before also. Okay, so now you can see these are the contours for velocity. Okay, so you can run this code independently. I will be uploading this code. Okay, and then uh, be sure, now you can see that these results are good. Okay, I mean, in if you see with the benchmark also, this is how the contours will come. Okay, but the only thing is that uh, yeah, slightly out the boundaries it might be inaccurate, because I have not exactly implemented that ghost thing. Okay, so yeah, so that you can implement and check the code. Okay, but you can compare these results also with the benchmark results. I think this should be enough. And I have run it with a very coarse grid now. Okay, just to show you result, just taken 30 cross 30 grid. Okay, you can take maybe 100 cross 100. You'll get much more accurate results. Okay, so that's it for today's class. Any doubts with respect to coding? Any doubt with respect to question and answers? Any doubts with respect to overall content? Uh, you can ask. Okay, unmute and ask.
So what is divergence free? Uh, it's a similar to divergence condition.
Uh, with respect to what you are asking me, divergence free, I did not get, because there are many things like divergence means many things. Where did you find this divergence free?
If I basic in assignment, so
Huh?
similar.
Okay.
Okay, I'll tell a term.
Huh?
Navier-Stokes equation is divergence free.
Navier-Stokes equation is divergence free.
For the intermediate velocity.
The intermediate velocities. No, they are not divergence free. That is what I was telling here, no? So divergence of u star, it is not equal to 0. So it is not divergence free. Whereas divergence of un plus 1 will be equal to 0. So it is divergence free. You understood? So for
So,
intermediate
sir,
velocity, it is not divergence free.
what I was trying to
Huh.
mention is that what is the term divergence free?
Divergence is equal to 0. Divergence free.
Yeah, same as divergence condition, right?
Yeah. So basically, divergence of u equal to 0 means it doesn't have this divergence term. So it is equal to 0. It is divergence free. So if you say un plus 1, the final velocity which you get is divergence free. The intermediate velocity which you get is not divergence free.
Okay, sir.
Yeah.
Sir,
Yeah.
I have one more doubt.
Mm.
A few doubts actually.
Mm.
There is properties for numerical scheme. What is conservativeness, convergence, and boundness? Oh, sorry, conservativeness, boundness, and transportiveness.
Mm.
So in that there is a Beckett number, which is
Mm.
the
Mm.
ratio of con-
Convergence to
conversion by
diffusion.
diffusion. So in the lecture, it was told that if there is no diffusion, the Beckett number will go to zero.
I think infinity, no?
Yeah, it should be infinite, right, sir?
Because you have very high convection. If you do
In
not have convection, then it is 0. Peclet number is 0 because it basically determines Peclet number how good is your convection. So if convection is not there, then it is 0. But if there is no diffusion, only convection, then it is infinity.
yes, sir.
It should be infinity, yeah. And
Uh,
sometimes Peclet number is infinity, yes.
so there is a small diagram which I was not able to understand from that. I will just mention the if I'm able to get that slide.
Do you
Okay,
remember the?
page number 167 of the transcript.
Wait a minute, I'll just close this MATLAB. This will take too much memory. Two? What did you say?
167, sir. Page
167. Huh? Hmm. Yeah. So if there is no diffusion, no, I think Peclet number should be infinity. Yeah, but whatever statement is there given, then the conditions at P are influenced by source at W and E. That is correct. That is correct. Oh, sorry, that is not correct, I think. if there is no diffusion and if there is only pure advection, uh, then it should be either influenced by W or I think what they meant was convection actually. That if there is no convection, then P is equal to 0, and then conditions at P are influenced by both source at W and D. So, if there is no diffusion, it means there is some convection. Whenever there is convection, the conditions at P are only influenced by dominant flow direction, usually direction of the flow.
So what if these two circle actually represent those are sources?
So their influence, I think.
So the P should be on the east side, right?
No, 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 no. See, direction of flow they have given from left side, na. So P should be influenced by W in that case.
Oh,
Hmm.
oh, P, W, they are like nodes.
No, I think what they have really given the diagram also here is for no advection. What do you say? No convection. Okay, this diagram is for no convection actually, because here they are trying to tell that both have the influence at P. That is what this diagram indicates, right? Like E also has a impact and W also has a circle which has impact. So if P is 0, but it is for pure diffusion case when there is no convection in it. So this diagram you understood, na? So see, if this W had a higher radius and if it crossed over P, it indicates that P has only influence from W or more influence from W. If that was the case, if there was a higher circle, a higher radius circle. But here the radius of both the circles are same and they are coinciding at P. It means that P has influence from both W and D. That can happen in pure diffusion case. And P Peclet number is 0.
And so basically those two circles are sphere of influence.
Sphere of it. Yes, exactly.
Okay, I understood
Hmm.
that. Sir, my next doubt is basically on quick scheme.
Hmm.
I was not able to compute the numerical problem from the assignment as well.
Hmm.
Especially for the near nodal thing,
Hmm. Near node, I think
near boundary. Sorry.
near boundary you cannot apply. Near boundary you can apply only till second order of point, I think. That is what I have seen in some of the CFT textbooks. So usually they go with a mix of things when you are applying quick scheme. In my code also, in one of the code I had implemented a quick scheme, but when I came to the near to that boundary grid point, usually we call it as border grid point. So we have boundary, border, and we have internal grid points. So when I am in the border grid point, which is close to boundary, I do not go with a quick scheme. I usually implement a second order of point there. I think you cannot calculate the coefficients or something like that.
But there is a numerical system for 60.
Hmm. I don't know how that is done because you need at least two upstream points, right? For that. If you don't have two upstream points, we go about. I don't know because I have seen in textbook that one of the textbook which I read that you go with a mix of things. You have to implement SOU, the border. It's no quick scheme. In SOU also coefficients will change for border. It's not the same for internal grid points. The the weights will change, but you can implement a SOU. I don't know how you can implement a quick scheme. Maybe you can ping me on my mail. I'll go through that textbook once again because there was a discussion on this. I don't know in this weekly content there is no discussion on that I think, but in a textbook which I read, there was some discussion regarding this. They also had told how we can change the coefficients to obtain the scheme at the border grid point. Okay, so I'll again go through that book and maybe I'll let you know. You can ping me
So,
on my mail. Okay.
So I can send you that question by mail.
You just tell me, you just send me a mail and tell me that this is your mail ID and you had asked me this question. I'll reply.
Okay.
Hmm. Any other queries? Yeah, yes. Go ahead.
Sir, you mentioned about that you are sharing on drive. So how to access those drives?
Okay, I had actually told this in the earlier class. I can again share it. Okay. Thanks for asking that question. I actually wanted to share that information. Let's do it. So this is YouTube videos you are able to see, na? My YouTube videos.
Yes, those there on the
Okay.
YouTube.
I have uploaded all weekly contents, also slides, codes, everything. I'll share that link on a Google Drive. Okay, I have shared the link. You can copy paste and keep it somewhere in Notepad. Okay, because this link will expire once the meeting is ended. Okay, just save this information. So there in that Google Drive, you will find all the weeks, week 1 to week 8, everything. I would suggest that you people at least do some experiments with the code. At least today, what I taught you, okay, the code. Just try to see how you can implement that ghost method, and you will get some minor improvements in the accuracy, but overall the results will be same. Okay. Okay. So yeah, any other queries? Yeah, so this is your last week, so you can maybe comment on some uh, general things which you observed in the course, like uh, first of all, let me know how was my teaching, like did I really go fast, or like whether the things which I covered, like the tutorial problems, was it less, or the MATLAB coding you were able to follow or not? Can you just comment? Yeah, yes.
Sir, actually, first of all, thanks for this all these sessions. Sir. It was really great.
Yeah,
We
yeah. Thank you
I
for
can say
attending us.
for my, I never miss any of the sessions.
Yeah, yeah, I think so. Yeah,
Just one thing, if I
yeah,
uh, instead of sir using mouse, if you can use a digital pad, it will
yeah,
be more clear. Guys,
yeah, yeah. I
how
will
to
have
note
that.
down.
Yeah. Actually, I am
Let's see.
planning, I mean, not for NPTEL course, I am planning to do something for computational methods in general thermal and fluid engineering. I am planning to again like create a lecture series. There, I am definitely planning to use something like that, because I also know with hosts also becomes very odd, like all scribbled here and there. Yeah, yeah.
Because
Thanks for that.
I share these videos with my colleagues, so
Okay.
they they were just pointing out, okay, what
Yeah,
it could have been.
yeah, yeah, yeah. Definitely.
That
Thank you
is
for
good.
that. Yeah. Okay. Thank you, Siva. Okay. Yeah, I asked. Okay, fine.
Yes, sir.
Huh. Nothing, nothing. You had, I saw that you had raised a hand. Okay, I think you lowered it. Okay, so with this, we will come to the end of this course. Okay, thanks for thanks to all of you for joining. First of all, it's very hard to even watch a movie sitting continuously for 2 hours nowadays. You were sitting for 2 hours watching my lectures. So yeah, thanks for that. Okay, so mainly on exams. Okay. Uh, About the exam pattern, I really don't know, but you see, you will not get purely MCQ questions. I know for that, and then you will have like a mix of questions wherein some of them will be mathematical. So that is what I was telling. The solutions to linear equations. There you can expect a mathematical questions wherein you will be asked to say you will be asked to link up everything whatever you have learned. Say for example, I can give a question. Say you have to solve a 2D heat conduction equation without any heat generation, steady state. Okay, then that is a problem you have. Okay, now solve it using say Gauss Seidel method till you get iterations for till you get the results for four iterations or five iterations. So you have to come up with everything. You have to first write the PDE, okay, then apply the second order central difference, then convert it to linear algebraic equation, then see what is AP, AW, AE, okay, and for this number of grids, okay, then set the linear algebraic equation, then apply Gauss-Seidel method. So this is like whatever you have learned from like week 3 to week 7, something like that, they will be compressed into one question, okay, something like this, okay. And then yeah, you can expect like something, some sort of those questions where things are a bit of mixed up, okay. And then you can be asked like what are the like these differences between the different algorithms which you see. These are some kind of descriptive questions, these type of questions which you can get, okay.
Descriptive question in the sense like it's a computer based question.
Okay, you will be
Or
having all MCQ questions, because last year I don't know, I had seen some descriptive questions somewhere. Have they told that it will be all MCQ?
No, sir, it's MCQs, then fill up the blanks and some essay type.
Essay type, na? Huh, that is what I am telling. Okay, but it is
essay type.
computer exam, so correct. So I don't think that mathematics will be asked too much. Yeah, then you can expect theory questions only, even if there is a essay type, because
So
mathematics.
where the essay type? No, essay type is basically for online test, right? Offline test, right?
I'll have to
No,
see
for the
because
MCQ.
because I have seen somewhere this kind of questions. Okay, that's why I was saying. Okay, but I don't know exactly which exam was it. Okay, just see the pattern. So if see if there is something like this essay type question, then you can expect these questions. Okay, what I'm telling. But if it is all pure MCQ, fill in the blanks, I don't know. Even in fill in the blanks, they do can ask. Actually, in MCQs also they can ask, but they should at least give high marks for that. Like what question I had asked. Okay, such questions can be asked even with MCQ, but really the weightage should be high. But at least you can expect such questions. Is what I'm telling. Okay. Okay, so I hope that you have kind of got something out of these tutorials. Like at least I wanted to personally share something related to coding, because exams will be there always, some exams will here and there, but you have to learn something out of a course, and at least for this course it's coding, I would say, nothing else matters, okay. This theoretical knowledge will be there. See, I only did not know what is CFL full form, okay. I have been using it like since many years, okay. So those things will be there, you will not remember those things, but yeah, at least you have to know the concept and all those things, okay. Yeah, so yeah, thanks for attending, okay. If you have any queries, you can stay. Otherwise, can leave the meeting. Okay. Please recommend some books for coding to learn open form. To learn open form, books are not needed. Okay. If you really want to learn open form, and first you should not directly go into coding when you are learning open form. Okay. There is a systematic way. You should learn the software in general as a whole, just like how you learn ANSYS and all, although it is different, it's completely different open form, but you can learn it something like that on that level by just watching videos, okay. And then the second step will be when you want to extend the open form solvers. So you have something like ecoform, piezoform, incompressible form, and piezo algorithm based form methods and all. Now when you want to extend those methods, you will get into coding, and that is very and that happens very rarely. And if you want to have some multiphysics, okay, if you want to model a transport equation, you will get into coding. Now the coding is C++ in open form, okay. Now the first way is you have to check out this website, okay. uh, I am just writing it on the chat box, okay. These people, like I also have for some time worked with these people. It's a FOSSE team in IIT Bombay, and they have created a wonderful web page, and they have kind of shown many lecture videos. They have given many spoken tutorials on open form, okay. There is a lot of material on open form. These people strictly work on open form, okay. For say IITB CFD, you can search something like this, you will get their website, and there are many resources. Even there is one of my 8 lecture series in this. wherein I myself have given some tutorials on OpenFOAM. Okay, so you can go through this. It's not much related to coding. So once you kind of understand this, then you have to go through the manuals of OpenFOAM. Okay, OpenFOAM wiki page is also there. Okay, so there you will learn everything. There is a manual. It's like a book only what you are asking. Yeah, that's the only thing. Okay. Next course, I don't know whether you have something course like this computational methods for thermal and fluid engineering or something like this. This is a more generalized course wherein you will be learning, and in especially in CFD perspective, there are many courses, but they run on the same line. I myself was a TA for this other course in the previous year. That was a aerospace course, AE20 Introduction to CFD. There also many of the things overlapped, but they were much more focused into hyperbolic equations because aerospace people do solve hyperbolic equations. Okay, so for supersonic flows and all. Okay, so it gives you a different flavor altogether if you are taking a course from a different department but on the same subject. Okay, CFD subject only but from a different department. Okay, you can try that also, and maybe some computational methods course. Okay, and then there is one course I think which you all must definitely go through. Okay, it's a continuum mechanics course. Okay, see this all these equations whatever we are deriving, they are based on the principle of assumption of continuum. Okay, and these continuum approximations are not valid in microscale flows and all microfluidics and all. Okay, but in many of the other situations they are valid, and with only with this principle it's like a theory for everything. Okay, with the same continuum mechanics principle you can derive the equations for computational structure dynamics, computational acoustics, sorry, only for acoustics or structure dynamics, whatever is there. Okay, it's a computational mechanics course. I would suggest just go through that course. I don't know who is teaching that. Okay, but there is a course I have seen that there is a course on continuum mechanics. Okay, so these are the courses. Okay, again thank you for attending. So if you do not have any queries you can leave the meeting. Okay.